Full room here because we got something for everything, something for everyone here. You know, if you're not too familiar with WMI, maybe you think the product's name is actually WhyMI So Sexy. That's okay. You're in the right place. We got you covered. We'll teach you what it is. For the red teamers in the room, we're going to be teaching you some really neat techniques here. In my experience, I've seen no organizations that are ready and prepared to deal with attacks that highly leverage WMI. And are there any blue teamers in the room? If there are, did that last statement kind of scare you? No. Good. That's a good attitude to have. But if it did scare you, we got a lot of information for you as well to deal with attacks in real time, to actually have an active defense, and then also to do offline investigation after the fact, figure out what happened. So we got a lot of information to cover. I don't want to spend too long on this. I don't know what just happened. It was probably China. Easy enough. All right, Matt, so want to give us your insight into this?
Yep. All right, so let's jump into a demo of an attack. Well, first of all, so you've been owned with WMI. What do you do next? Well, first of all, would you even know if you were owned with WMI? In reality, there's very few organizations, as Willie said, who would actually be able to, one, detect that they were owned with WMI and then properly remediate after the fact. All right? And until recently, so recently as in Vegas, there was no forensic, like dead disk forensic parsing capability. Fortunately, we have some awesome parsing utilities now that can extract some really valuable forensic artifacts from the WMI repository. All right, and then I would say that there's kind of a general lack of awareness of the offensive capabilities of WMI. So I hope to share some of those to you. And also there's very few actual defensive capabilities, but there are one or two great ones out there already. But let's look at a quick demo here. So here in this fictitious attack, what I'm going to do from my attacker's machine, the red VM, is remotely install a credit card track data scraper onto my victim using nothing but WMI. So the trigger for this payload on the victim machine will be whenever payment processor.exe is started on the victim, it will launch this payload. And so all of this is persisted remotely and installed remotely. So now in our victim machine, here's our fictitious payment processor.exe. I'm just going to paste in some fake track data, fake but valid track data. So now the payload has executed, unbeknownst to the victim, and it's running through all the pages of memory, parsing out all the strings, and if it detects that the regex matches, then you'll get some nice, pretty output that you'll see here. And it's nice because it'll be like a fully parsed, pretty PowerShell object. So there we go. Okay, so you were just owned with that. So how would you go about detecting that and go about mining forensic artifacts from that? We're gonna cover that. Willie?
Yeah, I'm not going to spend too much time on introduction here. My name is Willie Ballantine. I'm a reverse engineer. I have some background in forensics, running. I'm learning how to skateboard, stuff like that. Let's get on to the good content.
Cool. I'm Matt. If you don't already know, I'm kind of a PowerShell fanboy.
I'm Claudio Teodorescu. I don't recognize my middle name, and actually that's not a nickname. It's my English translation of my name. So... And I'm part of the Flare team as well as these two guys. I'm a forensic researcher. I work for Guidance Software doing encase parsers for 10 years, and now I joined the forces with these two guys and doing cool stuff. And I wanted to be a soccer player, but my parents had a different idea, so here am I. So now I'll talk the outline of our talk. So first we'll go into some background, motivations, and attack examples, some WMI basics, which architecture, the query language that WMI uses and inventing, and a brief history of WMI malware and their attacks, a life cycle, providers, file format investigation, real-time defense and mitigations. We'll jump into the WMI forensics. And we have a mock investigation of the credit card memory scraper, and then we'll talk about defense and detection.
Cool. All right, well, let's cover the basics. I'm sure most of you already know what they are. You know what WMI is. You've probably used PowerShell to interface with WMI, or WMIC.exe. It's really popular amongst pen testers. But so what is it? So Windows Management Instrumentation, basically it's just a really powerful local and remote administration framework. So you can use it to mine all kinds of really useful information to both an attacker and a defender. All right, so you could use it to remotely obtain registry keys, do file listings. What's great is that, so WMI is, it's like a very object-oriented language, so you can, there's a ton, well, there's thousands of built-in WMI classes, and you can create your own. So many of these objects also have methods associated with them. So a really popular one amongst attackers is the create method. It's a static method in the Win32_process object that enables you to execute code remotely. So it's really, really powerful. So there's a bunch of other valuable methods as well. Sort of the killer feature to me for WMI is it has this whole like event subscription mechanism. So you can do it both locally, like say you want to do it like just in the context of PowerShell.exe, but you can also you can do like permanent WMI subscription. So this is a great persistence mechanism for attackers, but also defenders can leverage it to their advantage as well. And as is the case with anything, you know, if you have a tool that's really valuable to administrators, then you know. Chances are it's going to be really powerful for attackers as well. You know, so something like PowerShell, you know, great for administrators and defenders, also a great tool for attackers. Now, there's a ton of different ways to interact with PowerShell. I'm not going to enumerate every single one. So, you know, there's WMIC.exe. You can interface with it in VBScript, JScript. If you were to write like C++ code, there's like a COM interface that you can use to interface with this. Now, I'm not just saying this because you know I'm biased and I'm a PowerShell fanboy, but interacting with PowerShell, with WMI and PowerShell is extremely powerful. So right out of the box, going all the way back to PowerShell version 1, you have all of the WMI commandlets, the ones that you see at the top there. So you can use these to enumerate objects, execute WMI methods, register events. All right, so as an attacker, that's pretty much everything you need. There was some functionality extended beyond those commandlets in PowerShell version 3 and above with the SIM commandlets. So they basically allow you to do the same thing. The biggest advantage to using the SIM commandlets is if you're in an environment where they're using WinRM or PowerShell remoting, these commandlets can run over that protocol in addition to the legacy protocol, which is DCOM. Okay, let's talk a little bit about the query language for WMI. So WQL, it's a very SQL-like language. It's pretty simple. So it can be used to basically do two things: to enumerate object instances and to register events. All right, now there's three classes of WMI queries. There's instance queries. So say you wanted to enumerate instance, like get a listing of all running processes. So get all instances of Win32_process objects. We can register events, and we'll dig into those briefly. And then there's meta queries. So if you want to learn more about how the SIM repository or WMI repository is organized, you can use a meta query to like list out all the namespaces and classes that might be available to you. All right, here's what an instance query looks like. So I'll just jump right to the example where, so you say select star meaning I want you to return all of the properties of what object? The Win32 object. And then optionally you can add a filter onto that where the Win32 .name property contains the string Chrome. All right, so it's just a process listing of all the Chrome processes is what that's doing. Now we can also register events. I find these to be extremely powerful. You can get very creative as both a defender and attacker here. So let's look at the first example. So select star from instance creation event. So this will trigger and return all the properties of any WMI object that is created Now we're going to have a filter on that because there's so many objects that are created all the time. So that filter being where the target instance is a Win32 logon session. And target instance.logon type equals 2. Can anyone tell me what this is going to trigger off of? An interactive logon, exactly. Yep. So the second example here, select star from Win32 volume change event where event type equals 2. No, this is not going to trigger upon you, turning the volume up or down, right? So can anyone tell me what this does here? What this will trigger off of? Yeah, so when a disk is mounted, but specifically event type equals 2, if you look it up in MSDN, this will trigger upon insertion or removal of removable media. All right. The last example here is pretty straightforward. So, but this is an extremely valuable query for defenders for obvious reasons. Okay, eventing. Let's dig into this a little bit more. So, you've already seen a few examples, some practical examples of how you could use these event queries for good or evil. You can get extremely creative. So if you just take like your default like Windows 7 machine and enumerate every single object installed in there, it's well over like 7,000 objects. So you can get super creative here as an attacker or defender. Now, there's two like registration mechanisms for WMI events. There's like the local context. So you could call like invoke or register-WMI event to register an event within the context of PowerShell.exe. But you can also do this in a persistent fashion, so it will persist across reboots by using permanent WMI event subscriptions. So these require three things. A filter, which we've already seen, it's just that WQL query. So that's dictating like, okay, what is it that you're interested in triggering off of? And then the consumer. What is it you want to do upon triggering that event? And then a binding, or a filter to consumer binding, is just the registration mechanism that binds the consumer to the filter and actually installs that permanent WMI event subscription. All right. There's two event classes. So there's intrinsic events. These are events that are built into every WMI namespace. So like one of the well-known namespaces is like root simv2. There's a lot of great stuff in there. Within there, you would see all these intrinsic events. So take, for example, instance creation event. So when a new process starts, there's going to be an instance created of a Win32_process object. Okay, so you could tie into the instance creation event and then do something interesting based on that. Then there, say like file creation, modification, or deletion. There's going to be an instance creation, modification, or deletion event that occurs whenever a file is created, modified, or deleted. Now there's extrinsic events. These are kind of specialized events. They're not present in all WMI namespaces, but these are very like highly performant event classes that will trigger immediately. So one of the differences between extrinsic and intrinsic is that you have to specify a polling interval for intrinsic events. And I think the reason behind that is because the intrinsic events fire constantly, all the time. So it would bring your system like to its knees if you had some event consumer that launched some process upon a sim data file instance being created. So these are kind of specialized ones that fire immediately that don't require that polling interval. So you have some valuable ones like Win32 process start trace fires immediately upon a process being started. Module load trace fires upon any DLL executable device driver being loaded. So you can get really, really creative here. So then there's the consumers. What is it that you want to do upon the event firing? So there's 5 built-in consumers in Windows. Some of these should be obvious. So you have something trigger, and then you can have event data be appended to a log file. And then there's ActiveScript event consumer. So upon triggering something, execute VBScript or JScript. All right, attackers love this. NT-event log event consumer, SMTP event consumer, shoot off an email, and command line event consumer. Obviously, attackers love this as well. So imagine invoking like PowerShell.exe. Insert your payload here. Okay, so just as a reminder, this is the registration mechanism for persisting your WMI payloads. You need the filter, which is the WQL query, a consumer, what it is that you want to do from an attack perspective. It'll probably be active script event consumer or command line event consumer, and then the binding to actually register it. Okay, so let's talk about attack history. So the earliest attack that I'm aware of publicly that used WMI was Stuxnet. Now, it didn't really leverage Stuxnet in like the traditional context where, say, it executes some command at like system startup. So what they did was they used it as a privilege escalation. So back in the day before Microsoft fixed this was Stuxnet, one of the, I think it was like the printer spooler vulnerability. It was like an arbitrary write vulnerability. So just imagine if you could drop a file anywhere in Windows to get code execution, what file might you create and where would you put it? So they had the clever idea of putting a moth file, which basically it specifies like, so you can use a moth file to do like permanent WMI event subscriptions. They drop that into the WBEM directory, and what Windows used to do was anytime a new moth file was created in there, mothcomp would come by and just compile that and automatically add it into the WMI repository. And it runs in the system context. So they use that as a pretty clever privilege escalation. Ghost was like the first like commodity malware that I've seen that was using WMI. It was just like a file stealer, so it would monitor for those like SIM data file objects. So like whenever a new file would be created or modified in the user like the user document directory, it would automatically exfil those out. And then WMI shell is pretty cool. It is the first instance where WMI was used as like a pure command and control channel. And the mechanism by which it did that was it creates WMI namespaces, and then it like stuffs the payload in there, and then calls the create method in Win32_process, executes that, and then saves the output of that command into another namespace, and then you can pull that back remotely. So I was kind of inspired by that and extended it a little bit, and I just added to PowerSploit. There's invoke WMI command, which instead of using WMI namespaces, it just uses the registry as a means to stage exfil and payloads. So check that out. And our good friends APT29 have been super active in using WMI. So I'll go in a little bit into what they've been doing. Okay? But from an attack perspective, there's very little that you can't do using nothing but WMI. And so from like your Windows 10 attack machine, say there's some like old crusty like Windows 98 or NT4 box sitting out there somewhere. The WMI service is listening on it. So there's like this rich attack surface, given you have administrator credentials to pop like any box in a Windows environment. So we can do stuff like reconnaissance. I've seen some malware use WMI for like VM detection, code execution, lateral movement, persistence, data storage, and C2 comms. All right. So I mean, this is by far not an exhaustive list of what you could do to perform reconnaissance. So here I'm just kind of listing out like some of the common things that malware will do anyway as a first step, as it's like reconnaissance step. Well, you have all of these rich WMI objects anyway where you can get all that information. So code execution and lateral movement, again, that create method is extremely valuable. So here I'm just invoking notepad.exe on some remote system. So, just replace notepad.exe with PowerShell.exe, dash encoded command, and then, insert your malicious one-liner stager here, sort of thing. Okay? So, again, for permanent WMI persistence, you need the filter consumer and binding. So, attackers love this. So here's an example of what the CDaddy malware was doing. So this was actually a full-featured Python backdoor where its persistence component was basically this PowerShell script, and then it just invoked PowerShell.exe to persist itself. It's not terribly sophisticated. In fact, they just ripped out the WQL query that I use in PowerSploit here in the query object. So all that's doing is it's going to trigger shortly after system startup. And all it's going to do is it's using the command line event consumer to simply execute the Python executable evil.exe. So not super sophisticated, But you would definitely want to be able to detect something like this. Now, WMI is a data storage mechanism. This is pretty cool. So I never even really considered that you could do this until we saw APT29 doing something similar to this. So what they were doing was creating a custom WMI class and then stuffing their payload into the names of one of the properties. So here, just imagine, replacing "this is not the malware you're looking for" with some base64 encoded payload, which you could then use the win32_process create method to pull that down, execute it, and then save the output into a property of another custom WMI class that you created. So that's exactly what APT29 was doing, and this is pretty cool. All right, so real briefly, WMI providers, these are the things that provide WMI all of its functionality. So when you enumerate all Win32 process objects, there's some DLL that backs WMI that has to actually provide that information and go enumerate all the processes and then populate those objects respectfully. So that's what these providers do. I don't know, I'd say there's probably 100 built-in providers. These are just COM DLLs. And until recently, we just kind of theorized, I can't imagine there's any malicious WMI providers, but that would be really cool. In fact, most of the built-in WMI providers obviously are all going to be from Microsoft. There are some third-party providers. For example, right here on my Lenovo laptop, Lenovo provides you or Chinese APT the ability to remotely set BIOS settings, flash the BIOS. So yeah, good stuff. So whether or not you consider that to be malicious or legitimate, I don't know. Anyway, so I reached out to some buddies of mine and I was like, hey, wouldn't it be cool if there were some actual legitimate malicious WMI providers? And so without fail, these guys went out and the day after, they wrote their own malicious WMI provider. So Casey Smith wrote a shellcode runner which runs in the context in the system context. So here's an example invocation of that, just to show you how easy it is to execute shellcode and as system with this provider. And then Jared Atkinson wrote his own. So he wanted to be able to list out all of the active network connections. But then kind of on the side, he created an additional method, the run PS method, which would just execute arbitrary PowerShell in the system context. So it's really cool. All right. So I've talked a little bit about the attacks. Now let's start investigating these things.
Yeah, so that's some really neat stuff. We can do whatever we want basically on an entire domain using just WMI. I wish we could say that we came up with this idea and we're like, hey, yeah, this is totally unique. This is what we came up with. This is not quite the case. In the past, I think approximately a year or so, we've worked a handful of cases dealing with this group APT29. This is kind of Mannion's internal name for what a lot of you may know of as the Duke family. C Duke, Cosmic Duke. Some people believe they're Russian, and they've been some of the most interesting investigations I've worked recently. And Carlos actually had a really good analogy yesterday, which was just perfect for this. And he was talking actually about, as a red teamer, going into an environment and actually encountering a pretty good defense, right? Where you pop a shell, and then a minute or two later, they actually shut you down. And then you have to be creative, and that's actually kind of fun, dealing with an adversary that you can respect because they have good skills, right? So this was an investigation where I felt that way, because these attackers, they knew what they were doing. They were using really, really good techniques. They were clearing event logs all the time. They were secure deleting all of their files. I have a feeling they had an index in the back end that noted down every single file they created. They could easily delete it after the fact. And they were also aware of what defenders were doing, all right? They were aware when we were finding their backdoors, identifying their network connections, and within days they would have new versions of things, new network protocols. That CDaddy backdoor written in Python, then all of a sudden the next week later they had a brand new implementation in .NET. It was totally weird, but they were moving very quickly. And so it was a fun investigation, because as we found these guys, as we deployed more interesting techniques, technologies, ways to detect them, they also ratcheted up their game. And this was very valuable to us because along the way we were able to gather a lot of that intelligence and understand how they were working. And some of the things that they were doing was using WMI extensively to first move laterally throughout the environment, all right? Getting from one system to the next system. Staging payloads remotely on those systems. stuffing data into the WMI repositories and using that both to execute new commands and capture the output. Now this is really interesting from a defender's perspective because all of these persistent events, all of this data that's stored via WMI, are not going to distinct files on the file system, all right? That would make it easy for us to identify. No, in fact, all of that data that's being tracked by WMI is stored in a single database. It's an opaque database that really no one knows how to process, all right? And so as a defender, you come in and you look at this box and you say, I do my timelining, I do my process listing, I don't see new processes, I don't see any new files, I don't see anything in the event log. You know, what else do I have to look at? And that was our situation there. It was very difficult to find it. But we were fortunate enough to have good network coverage and some interesting host-based technology, so we could see what the attackers were doing, the commands they were executing, and so we could track them down even though they were using WMI. And so the next question was, we know they're using WMI. How can we actually start looking at a much larger scale, where is WMI being used by attackers? And so an obvious thing we can do is use some of those WMI meta queries to inspect WMI itself to see what's going on there. We can actually see when new things are installed in the WMI repository, new persistence bindings, things like that. But can anyone see why that isn't a complete solution? Well, here's a good example. Well, if the system's offline, there's nothing we can do about it. We can't inspect the offline system because that WMI service has to be running. All right. Also, I feel a little uncomfortable when I trust the operating system to tell me everything about itself. These days, I mean, we're probably set. But next week, next month, six months from now, I think a WMI root kit would be really neat, something that filters out the data that's being returned by WMI, and you would be none the wiser. So although this solution was feasible, it didn't seem like a good solution. So we now think, okay, well, we have these database files on disk, and we know that these are the files that contain the interesting information. We don't know what to do with them, all right? So some things come to us naturally, like, hey, we can just run strings on these guys, right? Now, that's not forensics. Sometimes you get good results. You don't really know what you're looking at. And so for a long time, that was the extent of our ability to analyze these WMI databases. We could guess at the output. But when the attackers started storing large backdoors in the WMI repository, things that were like 50 kilobytes, 60 kilobytes, it turns out that the database operates on a page level. Those pages are 4 kilobytes in size, and the data actually gets stored all over the place. And so we had a very hard time reconstructing the incomplete backdoors. So that didn't quite work. Also, what we could have done, and we tried a couple times, is we could take the database from an existing compromised system, move it into a virtual machine, and then analyze it in that virtual machine. We can kind of create this Frankenstein system where it kind of, the WMI service on the VM is able to inspect itself. But that also made me a little bit uncomfortable because I don't know what Windows is doing under the hood in order to parse that database. I don't know if it's doing automatic repair of that database and removing evidence. I just don't know what it's doing, and that makes me uncomfortable. And so we set out to figure out what this database looked like and see if we could actually do real forensics on these dead boxes. So the things that we expected to find in these WMI databases are all those kind of basic WMI concepts. We're looking at namespaces, classes. This is the type of data that we can query for. Properties are specific features of a class. And the other things that Matt already kind of mentioned. So we're expecting this type of information. And we expect to find it in these few files listed on the screen here. Objects.data is usually a pretty large file, might be tens or 100 megabytes on your system, exists in this system root WBEM repository directory. And you run strings on it, you see a lot of really good stuff. But you open it in a hex editor, and you see that it's not a text file. It's not easy to interpret as a human. So for a long time, we just collected that files, and we ran strings on it. And we got somewhere at least. But that objects.data file doesn't exist by itself, and you cannot process it completely without the rest of these files. So this index.btr file is a B-tree index that allows you to quickly look up and query the objects database. And there's some additional files that provide metadata about this database. But still, we're dealing with this huge database, this huge 100 megabyte file. We don't know the binary structure. So we put our heads together. We spend a few weeks looking at this thing, and we reversed its entire database format. We know what every single byte means in the entire SIM repository, WMI database. All right? And this is really powerful because we can now do true forensics on these things. And I'll make a note just on the side here. Along the way, we actually didn't do any static analysis of the WMI service. Even though we're reverse engineers, we just understand assembly code, things like that. We didn't look at that WMI service. We didn't dynamically debug the operating system or anything. We actually just looked at the database files themselves and inspected them until our eyes bled. And then we did it again and again and again. But it was successful. If you want to know a little bit about how we did that, you can imagine we already know that there's interesting strings in there. So we kind of start with those. We say, okay, I know what that string probably represents. That's the name of a filter to consumer binding. Once you have a human readable string, you can imagine this must be pointed to by other data structures. So you start looking for pointers to these interesting strings. A lot of times these pointers fall within kind of a table of contents section that has pointers to many interesting objects. So you kind of work backwards from there. You also have to think, well, WMI provides all these various pieces of data. It must be able to query this information very, very quickly. So you start imagining how they must have designed the data structures when they were going forward with the engineering, and we just reverse engineered that. So we were pretty successful with that. And Claudia's going to take a few minutes now to walk us through some of those structures.
So, as Willie was mentioning, the most important parts of the WMI repository are the index.btr, objects.data, and the mapping.map. As you saw, there are up to 3 variants of the mapping.map, but only one is current, the other one are the backups. And the mapping.map contains the logical to physical map and the free pages map for both objects.data and an index.btr, and I'll explain how this is used. Both index.btr and objects.data are organized in pages. The page is 2000 hexa in size, or 8192. And let's take this example here in the index.btr. As Willie mentioned, it's a B3 on disk, and in the physical page 10, we see a B3 key that represents an evil consumer instance. And the key consists of multiple parts. The first part is the namespace to which the instance belongs. It's prefixed by ns underscore string. And then the next is the class, which in this case is a command line event consumer and is prefixed by ci underscore. And then is the instance itself, prefixed by il underscore. And the last 3 integers is the location record. The first is the logical page in the objects.data, where the data for the consumer instance resides. The next one is the record ID, and the next one is the size of the data in objects.data. So how the translation is done? We have the logical page, which is in this case 563. You go to the logical to physical map for objects.data, and we find out that at index 563 in the mapping, it's stored 230, which means this is the page, the physical page in the objects.data, where the record data for the consumer instance resides. So to find the physical offset, you multiply the page number with the page size, and you go and read the page, which is, as I mentioned, 8192 bytes. At the beginning of each page that contains records, there is a list of record headers. The most important things stored in the record headers are the record ID and the offset in the page and its size of the record. So you use the record ID that was in the B3 key to identify the record offset, the record header, and you get the offset in page. You add that offset in page to the physical page offset in objects.data, and you have the size both in the B3 key and in the record header, and you have the information about that consumer that you'll need to parse. Since I mentioned that index.btr, it's a B3 on disk, pointers to the next pages are represented as logical page numbers. So you have to use the mapping for the index.btr to translate the logical page to the physical page to get to the data of the children in the B3. Next, that's a parsed representation of a page in the B3. The red part is the strings, and then the next are the data structures that you combine to create the actual, you use to combine the strings to create the actual B-tree keys, and then another another red section towards the beginning. It's the pointers to the children, which are represented as logical page numbers.
So, who totally understood that? I mean, Claudia's... All right. Basically, we just want to demonstrate. We know what this thing looks like. We know how to parse it. And in fact, if you were interested in that, and that did kind of pique your interest, we have already released a white paper. It's almost 100 pages long right now that describes how to do this parsing, how to write your own parser, how to manually verify all those structures. So if that interests you, that information is online, and we'll have references later on. Anyways, so we did this reverse engineering. We figured out what the database looked like. The next step was to actually build tools around it, make sure other people could do it on their own. And so we've built 2 tools around this knowledge, all right? The first one I'm going to talk about is this Python sim project. This is a pure Python parser for these WMI databases. It's designed primarily as a library. It makes it very easy to develop short and sweet scripts that look for evil within WMI repositories. It's very easy to use. And the second one Claudia wrote is a C++ program, blazing fast, and it encodes a lot of the knowledge that we already have about how attackers are leveraging WMI and finds it automatically for you. All right, so you have a couple options here. But let me start by walking you through this Python library. Just to kind of demonstrate its capabilities, I wrote a small user interface around it, so we can kind of check that out. Let's see, how do I start this guy? All right, so here I am. I'm running on Linux, just demonstrating that it's a cross-platform tool. It displays the information in a nice tree view. It's very kind of intuitive to explore. At this point, we basically have what's almost like a file system. We can kind of browse through what are essentially directories and inspect the data. So here we are going through the sim v2 namespace, and down here, we'll eventually decide we'll pick the namespace root subscription. Now we're exploring, looking at our various classes. That's a very pretty snappy interface because we're able to use that B-tree index to quickly navigate to the data that we want to look at. So the data that we've decided to focus on here is this filter to consumer binding. This is what a lot of attackers use to maintain persistence on a box. So as we inspect this particular class, we can look at all its fields. One of the things we learned while parsing out this database is there's a bunch of additional timestamps stored in there. We suspect that these are the created and modification timestamps of objects. So when attackers are actually using WMI, this is another bunch of entries you can add to your timeline to figure out when the attacker is active. Really interesting stuff there. We're also able to parse out each one of the properties, and that's the type of information that we can pull from each instance of a WMI object. All right. Now, one of the really neat aspects, at least in my opinion, of this tool is not only does it parse all the data for you, it tells you how it got there. All right. So any of these structures that you're able to browse in that tree view, it also parses out for you and shows you in a hex view. And so you can see why it's interpreting. Well, okay, so this is the indication related class. It tells you where it found that string, where it found the timestamps, where it found the properties. And as you can see here, we can browse that information at the bottom, and it shows us where that information is coming from. We can highlight various fields. If you do it in front of your boss, he really thinks you're doing a lot of work. But practically speaking, this is a good feature to have, because you can always go back and confirm actually what's on disk. If it doesn't make sense, you can go inspect it yourself and actually, okay, my database is corrupt. Now I know what's happening. Or you can say, I didn't know the attacker actually was active on that date, and I've confirmed it manually in the database. So that was exploring a class definition. We can also take a look at the specific instances of this class. These are instances of that persistence object. So these are our filter to consumer binding instances. We see a couple timestamps there when these instances were created. This was back in 2009. And additional aspects of the WMI namespaces and classes and the references among them. So essentially, all those queries that Matt was describing earlier in this talk, we can now do offline on an OS X system, a Linux system, a Windows system. We can use Python to do it. We can use C to do it. We now have this capability, and I think that's pretty neat. Let's keep moving along here. Claudio, you want to walk us through your tool?
Yep. So my tool is more from designed from an IR perspective to get to the information quick and dump whatever information is stored by an evil consumer. So first, it's a command line, and you specify the path to the repository that contains the three files, object.data, index.btr, and the mapping. And what I'm doing here, I'm looking for all the consumer instances in the root subscription namespace, and I found here a command line consumer named test consumer that starts PowerShell and invoke an expression of data that is stored in the payload under the Win32 underscore payload class. Next is an NT event log consumer. This is automatically installed by Microsoft, so it's legit, but don't take my word for, check for it. Next is another command line event consumer. It's called BVT consumer. This, again, it's legit one, but I saw malware overwriting this. So validate that it's the legit BVT consumer. Since the first one, the test consumer, was looking weird and might be evil, I'm taking a deeper look into that, and I see that there is a class Win32 payload with a property payload, and also I find the binding to get to the trigger that makes this consumer execute. So I see the filter event, the event filter named payment card processor launched, and I'm trying to see if I can take a look what it's doing to find the actual query that will trigger the event. So next I'm gonna look for a filter instance that is in a root subscription, and it's named payment card processor launched, and it's a WQL query, and it says select star, which means whenever the payment processor exe starts, the consumer will execute. So what consumer will execute, what it will do, will go and read the payload property from the Win32 underscore payload class, and right now I'm actually dumping the definition of that class, and I see a big blob of base64 encoded data, which is stored as a default value for the payload property. And you see here class created 7/27/2015, which is a good indication when the attack started. And now I'm interested in what this big blob of base64 encoded data is doing, and I'm exiting my tool, and I wrote a little tool to decode it, and it's actually the memory scraper, and what it does, it scrapes credit cards and places them into Win32 exfil in the property track data under root CIMV2 namespace, and then going back into the WMI parser and see what is storing in that track data. I guess you guys can infer. So looking there, the class was created on the same, around the same date. So again, an external tool to decode it. And finally we see that the track 1 of the credit card for Fred Smith, it's stored in that property.
Does anyone know the format of that data?
Yeah, it's a serialized .NET object. So that concludes my demo. That was format for drinking. Yeah.
All right, so real briefly, I'm going to cover detection of all this. So we've been talking about WMI eventing for a while now, primarily from an attack perspective. Well, from a defender's perspective, you can get really creative here. So almost every single interaction on the operating system can possibly trigger some kind of WMI event. So as a defender, start getting really creative, right? So for example, what you saw previously was the trigger was whenever a Win32 process instance was created, then that payload would execute. Well, how was that payload installed in the first place? Using WMI permanent events subscriptions, right? So what kind of artifacts might be present by going through that installation process? Well, you would have an instance creation event that would be triggered whenever you would have the filter to consumer binding, the event consumer and event filter classes being created. So as a defender, start thinking about how you might be able to detect these sorts of things. All right, so, I mean, you may begin to see a pattern here, right? So what I just said, like, why not use event consumers to trigger alerts on event consumers? You can totally do that in WMI. All right, so you could use it to detect WMI persistence, registry persistence, service creation, scheduled task creation, so on and so forth. All right. So WMI is a great solution for this. So it's the agentless IDS that you never knew you had, and it's totally free. Okay. So a while ago, I wrote sort of like a proof of concept post IDS. It's on this GitHub here. Don't use it. Instead, use Jared's uproot utility. So this is in active development. Like, he's actually developing it as a legitimate agentless host IDS. So it's a great tool. There's still a lot of work to be done, but he's abstracted it out such that it's really easy to add new signatures to it. So I really recommend that you check that out. He's done some great work, and he's a total hipster. All right. So the takeaway from all this is be creative. All right. Just because attackers are doing this doesn't mean that you as defenders, you know, are going to be left with your pants down if you can get creative here. So, all right, so just want to thank a few people. Will Schroeder, Justin Warner helped me out with some of the malicious ideas here. And then some of our Armenian investigators are the ones who brought all this WMI, all these capabilities to our attention. These were the guys who were, you know, in the field investigating APT29, so I'm going to give a shout out to them just because they're awesome at what they do. And of course, APT29 for your inspiration. You allowed me to steal some of your capabilities and integrate those into my own tools, so thank you very much. All right. So let's take maybe like 2 minutes for questions, and then I don't want to go over our time here, so any questions? Back there. No.
Yeah, you can do it, no problem. The only thing is the only thing that WMI does, the mapping, it says that is in a dirty state. So as long as you don't stop the service, the mapping, so you might lose some information out of there, but you can do without any problem. There is you don't have restriction to the pages of that are in the objects.data. The only thing is that the mapping, that data will say that is in a dirty state.
That seems like that would be an easy way to detect the low-hanging fruit way of doing it that you might forget, because you have to file system level otherwise, so that would be in the application.
One more question?
Seems to me that in both the tools you could do a compare, like go ahead and grab the WMI parser from the box, throw it into the box, and show me the data.
Yeah.
Yeah, absolutely. And I think actually the state that we're in right now is that there's literally thousands of these different WMI objects and classes and namespaces. And although we have some knowledge about WMI, we don't know everything that's supposed to be there and what's not supposed to be there. But it's trivial for us to write a diffing script now that we can... Yeah, exactly. We start with a gold image, look for differences, and just focus on taking a look at those. That's an easy way to start analysis.
Great. All right, thank you.
And also you can create your own providers that inject whatever data you want. So that's the problem, you know. You don't know what should be there. So that's why it's good to have a baseline all the time.